NGC 2685, also known as the Helix Galaxy, is one of the most peculiar and captivating structures in the nearby universe. Unlike typical spiral or elliptical galaxies, it defies conventional classification, presenting a bizarre, twisted configuration that astronomers describe as a polar ring galaxy. This rare form reveals two distinct components, a central lenticular or elliptical body, surrounded by a nearly perpendicular ring of gas, stars, and dust. The result is a gravitational ballet frozen in time, a warped, multidimensional sculpture that seems to rotate along two axes simultaneously. Its morphology suggests a violent past. The outer ring, rich in neutral hydrogen and young stars, likely formed from a collision or accretion event, where NGC 2685 cannibalized a smaller companion galaxy. Instead of settling into the plane of the host galaxy, the captured material stabilized into an orbit nearly orthogonal to the central structure, leading to the galaxy's current twisted shape. Such a configuration is gravitationally stable over cosmic timescales, defying expectations of rapid decay or realignment, which highlights the remarkable complexity and resilience of galactic dynamics. NGC 2685 is located approximately 42 million light-years away in the constellation Ursa Major. Despite its relatively close proximity, its true structure was obscured for decades due to our Earth-bound, edge-on view. Early observers believed it to be a simple elliptical galaxy with some internal dust lanes. Only with the advent of multi-wavelength observations and detailed kinematic studies did its polar ring nature become apparent. These insights were further enhanced by radio observations tracing the extended hydrogen envelope, revealing a disk in near-perfect perpendicular rotation to the central axis. The coexistence of two stellar populations rotating at different angles is a unique laboratory for understanding galaxy evolution and angular momentum transfer. While the inner component consists mostly of older stars and displays little recent star formation, the outer ring hosts regions of active star birth, indicating a dynamic interplay between stability and disruption. This duality allows astronomers to study how gas behaves when accreted in misaligned orbits, providing insights into how galaxies grow through minor mergers and cosmic infall. Unlike many more luminous or well-known galaxies, NGC 2685 emits relatively little in the infrared and ultraviolet, making it a subtle but significant player in the larger narrative of galactic transformation. The absence of strong active galactic nucleus activity also suggests that its central black hole, if present, remains dormant or underfed. This allows astronomers to examine the gravitational interactions without the confounding influence of energetic outflows or jets. Some simulations suggest that galaxies like NGC 2685 might represent a transitional phase, an intermediate step in the hierarchical assembly of larger galaxies. Over billions of years, the outer ring may dissipate, merge, or become fully integrated into the host body, erasing the striking polar features and leaving behind only faint relics in stellar velocity maps. Observing such a structure today is akin to catching a rare snapshot of a fleeting cosmic configuration, an architectural trace of collision and stability coexisting in precarious balance. Its isolation in the sky further deepens the enigma. NGC 2685 doesn't reside in a dense galactic cluster, reducing the likelihood that tidal forces alone shaped its form. This makes the accretion theory even more compelling, possibly involving a long-dead dwarf galaxy whose remains now trace a luminous halo in the polar plane. The stellar populations within the ring differ chemically from those of the central bulge, further supporting a multi-origin scenario. The question of longevity remains central to its study. The polar ring must balance against gravitational torques and precession forces, and yet NGC 2685 has maintained its integrity for hundreds of millions of years. Such endurance hints at a finely tuned dynamical equilibrium, where mass distribution, rotation, and orbital mechanics synchronize to prevent collapse. It may serve as a reference model for understanding galactic warps, misaligned accretion disks, and even the formation of polar disks in early-type galaxies throughout the universe. If the galaxy had a voice, it might speak of dualities, of being torn between two frames of rotation, two histories, two fates. The core remains stoic and motionless by cosmic standards, while the ring circles with a youthful defiance, tracing arcs of light across an ancient sky. The light we receive from NGC 2685 carries the signatures of both calmness and conflict. Spectroscopic analysis reveals stark contrasts between the chemical composition and stellar velocities in the polar ring and the central bulge. While the nucleus shows signs of population aging and metallicity enrichment typical of lenticular galaxies, the polar ring is abundant in younger, metal-poor stars and ionized gas, echoing a more turbulent and recent origin. This juxtaposition creates a living archive of astrophysical time, where one galaxy contains relics of two epochs, layered not chronologically, but spatially. Rotation curves derived from hydrogen line measurements unveil a beautifully choreographed contradiction, two rotating systems intersecting through gravity, yet remaining in stable alignment. The ring doesn't merely orbit, it precesses subtly, hinting at the slow influence of torques and mass asymmetries over eons. Such measurements challenge older models of galactic evolution that favored symmetry and simplicity, pushing astronomers to account for multi-spin configurations in both isolated and group environments. In terms of luminosity, NGC 2685 is modest. It doesn't blaze with the brilliance of active galactic nuclei nor flood the sky with the starburst frenzy seen in merging systems. Its beauty lies instead in its contradiction, subtle, understated complexity hidden within an apparently ordinary shell. Optical imaging reveals the wispy outlines of the polar ring wrapping like a luminous helix, while deeper exposures show diffuse arcs extending beyond the visible ring, suggesting that the structure may be even larger and older than first thought. The rarity of polar ring galaxies like NGC 2685 cannot be overstated. They represent less than 0.5% of all observed galaxies, and each known specimen offers a distinct configuration. This uniqueness makes NGC 2685 not just an oddity, but a critical piece of the broader puzzle of cosmic structure formation. By studying such systems, astronomers can reverse engineer the processes of angular momentum transfer, gas accretion, and dynamical stability. It also opens questions about dark matter distribution, whether the halo around NGC 2685 is spherical, triaxial, or flattened, and how it influences the orbital planes of such dramatically misaligned components. Advanced simulations aiming to recreate galaxies like NGC 2685 require fine-tuning and high-resolution modeling to match observed features. These models must account for not just the gravitational collapse and merger history, but also gas cooling, star formation feedback, and long-term orbital evolution. Despite technological advances, no simulation has yet perfectly recreated the full complexity and longevity of NGC 2685 structure, suggesting that nature still guards some of its secrets behind layers of gravitational subtlety. On a philosophical level, NGC 2685 offers a metaphor for resilience and multiplicity. It is a system that defies linear history, instead embracing contradiction as structure. It teaches that galaxies, like civilizations, are not always formed by isolated growth but by the layering of interactions, collisions, and reconnections. One orbit speaks of quiet continuity, the other, of a cataclysmic past now tamed into harmony. The galaxy becomes a cosmic palimpsest, its older structure overwritten not with erasure, but with luminous revision. Its study has implications beyond aesthetics or classification. Polar ring systems may help refine our understanding of halo mass distributions, galactic shape inference, and even the processes governing star formation under angular shear. The stars in the ring feel both the pull of the central mass and the collective torque of their neighbors, creating star-forming conditions unlike those in typical spiral arms. Such dynamics may mirror conditions in early galaxies of the universe, where gas often fell in chaotically from the cosmic web at skewed angles, forming misaligned disks and rings. NGC 2685 also provides a valuable calibration tool for testing observational techniques. Because it contains two orthogonal rotating systems, astronomers can probe projection effects, three-dimensional dynamics, and velocity field modeling. It's a natural testbed for verifying the accuracy of spectral decomposition, spatially resolved kinematics, and dark matter mapping. In this sense, it is both a celestial phenomenon and a scientific instrument shaped by the universe itself. As telescopes become more advanced, the insights gleaned from NGC 2685 only deepen. Instruments like the Very Large Array and the Hubble Space Telescope have peeled back layers of its structure, revealing not only the shape of its gaseous and stellar components but also the faint filaments and arcs that may extend far beyond the visible ring. Future observations with high-resolution integral field units and space-based observatories like the James Webb Space Telescope may uncover even subtler details, hidden star-forming knots, faint tidal streams, or traces of the original companion galaxy long since absorbed. What is particularly intriguing is how the polar ring interacts with the interstellar medium. The compression of gas along the ring's orbit appears to foster the formation of stellar clusters in periodic bursts, much like beads strung along a wire. These clusters can then be studied to determine their age gradients, metallicity variations, and kinematic histories, offering a detailed timeline of how the ring evolved after the accretion event. Each stellar generation becomes a timestamp, marking epochs in a slowly turning wheel of galactic transformation. The polar ring may also offer indirect evidence about the dark matter halo enveloping the galaxy. If the dark matter distribution were purely spherical, the ring's long-term stability would be easier to explain. However, observations suggest that triaxial or flattened halos might be more realistic, and the way the ring precesses, or doesn't, can help constrain these models. NGC 2685, therefore, becomes a natural laboratory not just for visible matter, but for probing the invisible architecture of gravity that shapes galaxies on large scales. From a cosmological perspective, galaxies like NGC 2685 are fossil records of a more chaotic, merger-driven universe. In today's relatively sedate cosmic age, such dramatic accretion events are rare. But billions of years ago, when the universe was denser and more interactive, these events were more common, leaving behind relics like polar rings, warped disks, and extended tidal tails. Studying NGC 2685 allows astronomers to infer not just its past, but the conditions of the early universe that made such structures possible. Even now, there may be subtle internal shifts underway. Low-level torques, magnetic influences, and internal instabilities may slowly warp the ring, pull it inward, or cause its star-forming regions to migrate. Over the next few billion years, this elegant duality could dissolve into a more homogeneous form, blending into the surrounding stellar population and losing its distinctive geometry. Like all cosmic structures, NGC 2685 is temporary, an intricate configuration frozen in a moment that we, by chance, are alive to witness. It's easy to overlook galaxies like this amid the grandeur of quasars, colliding clusters, and supernovae. But NGC 2685 is a quiet anomaly, a whisper in the cosmic chorus, telling a different story. It doesn't shout with brightness, but instead invites those who look deeper to find meaning in asymmetry and balance. It reminds us that the universe is not always elegant in the classical sense, but often in the way that chaos can evolve into structure, and that even in disorder, there is order waiting to be discovered. The Helix Galaxy, then, is more than a name. It evokes the spiral not of simple rotation, but of entwined histories, motion wrapped around motion, time coiled through space. It carries the legacy of encounters long past, yet still visible in the present. Each orbit, each ring of stars, each trace of cold hydrogen is a sentence in a galactic memoir written across millions of light-years. And in reading it, we uncover not only the fate of a single galaxy but echoes of how galaxies live, merge, remember, and change. In the delicate dance of NGC 2685, one finds echoes of cosmic memory, an enduring imprint of a past event so transformative that it redefined the very geometry of the galaxy. This is not merely a collision frozen in aftermath, but a living structure, still responding to the gravitational consequences of that ancient interaction. Every precessing star in the ring, every cloud of hydrogen tracing a polar arc, behaves as if it remembers the infall, the absorption, and the gravitational rebalancing that followed. The ring itself is not a perfect, uniform structure, it is subtly warped, slightly offset, and rich with asymmetries. These imperfections are not flaws, but fingerprints, evidence of the initial conditions of the captured material and the influence of the galaxy's mass distribution over time. Unlike spiral arms that wind neatly within the galactic plane, the polar ring slices diagonally through space, carving its own dynamic path as it weaves a halo of light and motion around the host body. It behaves as both a companion and a contradiction, gravitationally bound yet geometrically separate. The stellar populations within the ring span a range of ages, suggesting episodic waves of star formation triggered by internal compressions or weak interactions with the host galaxy's gravitational potential. These periodic surges of activity may be akin to galactic breathing: inhale as gas flows inward and condenses, exhale as new stars ignite and feed back energy into the surrounding medium. This cyclical rhythm adds another layer of complexity, transforming the ring from a passive remnant into an active stellar nursery, continuously reshaping itself across millions of years. The core of NGC 2685 remains enigmatic. Though lacking the violent outbursts of active galactic nuclei, its calm is deceptive. Buried within the central bulge is likely a supermassive black hole, modest by quasar standards, but still millions of times the mass of the Sun. Its silence may be temporary. Should new material eventually spiral inward from the polar ring, it could awaken with a new cycle of activity. In this way, the past, present, and future of the galaxy remain connected by gravitational bridges and slow drifts of matter across cosmic time. NGC 2685 challenges the very definitions we use to categorize galaxies. Is it a spiral? An elliptical? A ring system? In truth, it resists singular identity. It exists in a liminal state, between types, between histories. Its form is neither purely accidental nor entirely predictable, it is the outcome of a unique set of initial conditions amplified over eons. For this reason, astronomers often see it as a case study in galactic identity, how shape and structure are shaped by history, interaction, and persistence. As our understanding of the universe expands, so too does our appreciation for galaxies like NGC 2685. They remind us that the cosmos is not defined solely by its grand explosions or the luminous beacons of quasars, but also by its quiet complexity, its ability to maintain structure amid chaos, to balance competing motions, to evolve into something stable yet strange. They reveal that harmony in the universe is not the absence of contradiction, but its resolution. In its geometry, we read the language of dynamics; in its light, the signatures of transformation. It is a galaxy of paradoxes, stable yet warped, silent yet evolving, symmetrical yet asymmetric, solitary yet shaped by encounter. It invites us to look again at what seems simple, to reconsider what we think we know, and to wonder at the hidden choreography of matter and motion in deep space. NGC 2685 orbits not just in its own frame, but within our collective scientific imagination, as a symbol of what galaxies can become when disturbed, and how beauty can emerge from disarray. It is a cosmic reminder that even the most unlikely configurations can endure, balance, and thrive in the grand architecture of the universe. NGC 2685 is not merely an astronomical curiosity, it is a profoundly instructive and multidimensional structure that embodies some of the most intricate principles of galactic dynamics, angular momentum conservation, and the long-term evolution of gravitational systems. Its most defining feature, a nearly perpendicular polar ring orbiting an older, lenticular host galaxy, is not simply a visual anomaly but a direct consequence of complex astrophysical processes unfolding over cosmic timescales. The current structure of NGC 2685 is thought to be the result of a past accretion event, most likely involving the capture and gradual assimilation of a gas-rich dwarf galaxy. Rather than merging completely and uniformly with the central body, the infalling material settled into a stable polar orbit, defying intuitive expectations that such material should quickly align with the galaxy's equatorial plane due to torques. This remarkable orthogonal ring of gas and stars exists in long-term equilibrium, sustained by the precise distribution of mass and angular momentum in the host galaxy and its dark matter halo. What makes the system especially compelling to astronomers is that it violates the common assumption of planar coherence in galactic structures. Most disk galaxies exhibit a dominant plane of rotation. Any misaligned or inclined features are typically short-lived due to differential precession and dynamical friction. However, the persistence of NGC 2685's polar ring over hundreds of millions of years challenges these models. It implies that either the mass of the ring is low enough to avoid significant backreaction on the central potential, or that the host's gravitational potential is sufficiently symmetric and spheroidal to support such a configuration over long durations. From a kinematic perspective, the galaxy exhibits two distinct and decoupled rotational systems. The main body rotates along its traditional axis, while the polar ring traces an entirely different orbital plane. High-resolution spectroscopy has shown that these two systems remain dynamically coherent, with minimal signs of warping or destabilization. This dual-axis rotation makes NGC 2685 a natural laboratory for studying the three-dimensional structure of galaxy potentials, especially in the context of triaxial dark matter halos. Furthermore, the polar ring is not just a passive relic. It continues to exhibit signs of star formation, as evidenced by H-alpha emissions and ultraviolet flux from young, hot stars. This ongoing activity confirms the presence of cold, dense molecular gas in the ring, material that may have originated from the captured dwarf galaxy or from cosmic filaments intersecting the halo of NGC 2685. The spatial distribution of this star-forming activity, often arranged in knots or arcs along the ring, suggests the influence of local gravitational instabilities, possibly amplified by the shearing forces between the ring and the host galaxy's gravitational field. The chemical composition of the ring also provides critical insight. Spectroscopic measurements reveal a lower metallicity in the polar ring compared to the central bulge, consistent with the hypothesis that the ring formed from the accretion of a less evolved, more primitive satellite galaxy. This chemical distinction serves as further evidence of the external origin of the ring and highlights the role of minor mergers in contributing not only mass but also chemically distinct stellar populations to larger galaxies. In terms of mass distribution, the fact that NGC 2685 maintains such a coherent polar structure implies a non-negligible influence from its dark matter halo. Numerical simulations have shown that flattened or oblate dark matter distributions can support polar rings by providing a stable, extended potential in which inclined orbits do not precess destructively. This connection between dark matter morphology and observable galactic structure turns NGC 2685 into a valuable tool for constraining the shape and extent of dark matter halos, information that is notoriously difficult to extract in more symmetric, conventional galaxies. Moreover, the polar ring may act as a tracer of the angular momentum history of the galaxy. Its inclination, precession rate, and mass distribution reflect the initial conditions of the interaction and the subsequent evolution of orbital parameters. By modeling these features in conjunction with observed stellar populations, researchers can effectively reconstruct the merger timeline of NGC 2685, offering a form of galactic archaeology that reveals the timing, nature, and impact of past accretion events. The implications extend beyond the galaxy itself. NGC 2685 serves as a representative of a broader, though rare, class of polar ring galaxies. These systems are exceptionally useful for studying the interplay between baryonic matter and dark matter, the mechanics of galactic warping, and the environmental conditions that allow multi-spin configurations to persist. Their rarity underscores the uniqueness of the conditions required for their formation, and their stability suggests that the universe is capable of sustaining highly nonlinear configurations when specific dynamical balances are achieved. Ultimately, NGC 2685 embodies the profound interconnectedness of cosmic phenomena: gravity, angular momentum, star formation, and dark matter all contribute to its existence. It is a dynamic fossil, a relic of a complex interaction written in the language of rotation curves, metallicity gradients, and morphological asymmetries. In studying it, astronomers gain not only insights into one galaxy's peculiar structure but also broader understanding of the mechanisms that govern galactic diversity, stability, and transformation across the universe. NGC 2685, widely recognized as the Helix Galaxy, is one of the most extraordinary and scientifically valuable objects among the catalog of nearby galaxies. Classified as a polar ring galaxy, PRG, a rare morphological type, it defies the conventional structures observed in spiral and elliptical galaxies, offering a three-dimensional, multi-spin system that challenges traditional theories of galactic formation and equilibrium. What makes NGC 2685 especially significant is not only its rarity but its stability, its kinematic complexity, and the diverse astrophysical processes it encapsulates within a single system. The most striking feature of NGC 2685 is its orthogonally rotating polar ring, composed of stars, atomic and molecular gas, and interstellar dust. This ring orbits almost perpendicularly to the plane of the central lenticular galaxy. From a dynamical perspective, such a misaligned configuration presents a highly non-trivial case of three-dimensional angular momentum decoupling. In a typical system, differential precession would cause such a ring to warp, dissipate, or realign with the equatorial plane due to the torque exerted by the central potential. However, NGC 2685 demonstrates exceptional kinematic coherence and temporal longevity, maintaining the orthogonal orientation of the ring for over several hundred million years. Theoretical models and numerical simulations in N-body and hydrodynamic frameworks suggest that the long-term survival of the polar structure requires a quasi-spherical or mildly triaxial dark matter halo. A flattened potential would induce precessional torques that destabilize the ring, but in the presence of a near-spherical halo, the ring can stably orbit without significant warping. Therefore, the persistence of the ring in NGC 2685 provides strong empirical support for certain dark matter halo geometries, constraining both the halo's flattening parameter and its radial mass distribution. The prevailing formation scenario for the polar ring in NGC 2685 involves the accretion or tidal disruption of a gas-rich dwarf galaxy. Such events are supported by simulations that reproduce polar rings through off-plane mergers with inclined angular momentum vectors. During this process, the interstellar gas of the smaller companion settles into a polar orbit around the more massive host, cooling and collapsing to form new stars. The inner lenticular body of NGC 2685 remains relatively undisturbed, indicating a low-mass ratio minor merger, which limits structural damage while enabling significant mass transfer. Observationally, this hypothesis is corroborated by chemical and spectroscopic evidence. The metallicity of the ring is systematically lower than that of the host galaxy's central regions, indicating that the stars and gas in the ring originated in a less chemically evolved system. Additionally, line-of-sight velocity dispersion profiles and rotation curve asymmetry show that the polar ring is dynamically distinct from the spheroidal host, affirming the two-component origin theory. Despite the galaxy's overall quiescent appearance, the polar ring exhibits localized star formation, as revealed by observations in H-alpha, far ultraviolet, Galex, and infrared, Spitzer, WISE. These regions contain compact stellar associations and OB star clusters, indicating recent or ongoing episodes of star formation. The conditions in the ring are unique. The gas experiences differential shear, is subject to non-axisymmetric gravitational potentials, and exists in an off-plane geometry. These factors influence the Jeans instability criterion, modifying the threshold for collapse and fragmentation. Furthermore, the ring provides a rare testbed for studying star formation under inclined, dynamically cold conditions, which are distinct from the disk instabilities found in classical spiral galaxies. Models incorporating feedback mechanisms from supernovae and stellar wind suggest that the evolution of polar rings involves a delicate interplay between self-gravity, cooling, and feedback-driven turbulence. In this context, NGC 2685 helps refine models of nonlinear star formation thresholds and star cluster survival in dynamically complex environments. Galaxies acquire angular momentum through a combination of tidal torques during the linear regime of structure formation and subsequent mergers and accretions. NGC 2685, with its two orthogonal rotation systems, serves as a direct observational probe of angular momentum misalignment in hierarchical galaxy formation. The ring preserves the angular momentum vector of the infalling material, while the host retains its original spin. This spin misalignment provides critical constraints on cosmological models of galactic assembly, particularly in the context of cold mode accretion and minor merger statistics in lambda-CDM cosmology. Moreover, the spatial distribution and orbital structure of the stars in both the host and the ring can be analyzed using integral field spectroscopy, e.g., SARON, MUSE, to extract 3D velocity fields. These measurements are invaluable for reconstructing the orbital anisotropy, potential shape, and merger geometry, providing a backward reconstruction of the galaxy's dynamical history. Perhaps one of the most scientifically valuable aspects of NGC 2685 is its utility in constraining the non-visible dark matter component. The polar ring acts as a tracer orbit, sensitive to the shape of the gravitational potential. By modeling the ring's stability, precession rate, and radial extension, astronomers can infer whether the halo is oblate, prolate, or triaxial, and to what degree. Unlike traditional rotation curve measurements confined to the galactic disk, the ring samples the potential in 3 dimensions, offering orthogonal leverage on the gravitational field. This makes NGC 2685 not just an astrophysical curiosity, but a powerful tool for dark matter cartography. Future studies using neutral hydrogen mapping, HI with VLA or MeerKAT, and stellar kinematics, with Gaia and ground-based IFUs, can further refine the mass profile and shape of the dark matter halo, which remains a key uncertainty in galaxy formation theory. NGC 2685 can be understood as a galaxy in transition, a dynamically settled system still bearing the scars and structure of a formative event. It encapsulates several processes critical to the evolution of galaxies in low-density environments: minor mergers, angular momentum acquisition, multiphase gas accretion, off-plane star formation, and non-coplanar stability. In doing so, it bridges the morphological gap between classical lenticulars and more chaotic merger remnants, demonstrating that even highly unusual configurations can reach equilibrium. Such systems may have been more common in the earlier universe, where gas inflow from the cosmic web often occurred along misaligned filaments. Therefore, NGC 2685 may represent a local analog to early universe galaxy dynamics, where rotation planes and inflow vectors were not yet aligned, and angular momentum was still being sorted across nested structures. By studying galaxies like NGC 2685, astronomers gain a glimpse into the nonlinear, stochastic nature of galaxy evolution, where form emerges not from simplicity, but from the resolution of chaotic interactions into lasting structure. NGC 2685 continues to intrigue astrophysicists not only because of its apparent uniqueness, but because it exemplifies how galaxies encode memory across billions of years. The interplay between the central lenticular core and the polar ring suggests a finely tuned dynamical architecture, where forces that normally compete instead coexist in a state of near-harmonic balance. Every orbit within the ring experiences both the pull of the central mass and the global influence of the surrounding dark halo, resulting in a motion that is neither chaotic nor trivial. This dance is further stabilized by the distribution of angular momentum, which must be delicately partitioned to prevent destructive resonances and warping. Such equilibrium is not accidental, it is the outcome of complex initial conditions, possibly only achievable through a very narrow set of merger parameters or cosmological infall angles. Simulations attempting to replicate this configuration often require precise initial orbital inclination, velocity dispersion, gas fraction, and host galaxy morphology. The success of these models is judged by their ability not just to produce a ring, but to maintain it with the correct kinematics and spatial extension over gigayear timescales. Deep imaging of NGC 2685 in optical and radio wavelengths reveals faint extensions and low surface brightness features beyond the main polar structure, suggesting that the galaxy's outer halo may still be perturbed or contain remnant material from the original merger. These features are vital, as they act like tidal fossils, recording the orientation and gravitational interactions of the past. Their morphology, luminosity profiles, and spectral lines help constrain the epoch and geometry of the encounter. Some of these arcs may be stellar streams or caustics formed by disrupted components of the captured galaxy, their motion slowly phasing into the broader halo. If properly traced and modeled, they could even allow a reconstruction of the original satellite's mass, orbit, and disintegration timescale. This turns NGC 2685 into a galactic time capsule, a structure whose current morphology encodes the detailed history of a minor but transformative merger. The polar ring also serves as a natural experiment in non-equilibrium star formation. The fact that stars continue to form in a structure that orbits nearly perpendicular to the galactic disk suggests that gravitational collapse and feedback operate effectively even under extreme geometrical and dynamical constraints. Local density enhancements, possibly induced by tidal interactions within the ring or by vertical compressive forces, may act as seeds for molecular cloud formation. These conditions differ significantly from those in spiral density waves or galactic bars, offering a complementary regime for testing models of cloud collapse, magnetic field alignment, and initial mass function variations. If star clusters in the ring are found to differ systematically in size, age spread, or chemical composition from those in the central galaxy, it may provide rare insights into how environmental factors shape stellar populations. The gas content of the polar ring, particularly the ratio of atomic to molecular hydrogen, remains a key diagnostic. High-resolution HI and CO mapping can reveal the thermal state, phase transitions, and turbulent spectrum of the gas, all of which influence its propensity to form stars. Measurements of line widths and velocity gradients across the ring may indicate the presence of shocks, shear, or hidden substructures like filamentary inflows. Such processes are relevant not only to NGC 2685 but to broader questions about how misaligned gas inflows behave in galaxies at high redshift, where cold streams were more prevalent. In this way, the Helix Galaxy becomes a bridge between the calm, structured universe we observe today and the chaotic, rapidly evolving conditions of the early cosmos. Beyond its scientific applications, NGC 2685 challenges visual and conceptual expectations of galactic form. It invites a rethinking of what it means for a galaxy to be stable, for motion to be ordered, for structure to persist. Its morphology is not a product of simplicity, but of resolved complexity, a configuration that is inherently three-dimensional, layered, and historically contingent. Its beauty lies not in symmetry, but in the coexistence of seemingly incompatible motions, held together by the universal laws of gravity and momentum conservation. It is a structure that forces one to think in rotating frames, in evolving potentials, in histories that do not align but still intertwine. To observe such a galaxy is to witness a system on the edge of transformation, not in the midst of chaos, but resting in the delicate pause between dynamic phases. Whether the ring will dissipate, thicken into a diffuse halo, or eventually collapse inward to feed the central region remains uncertain. But in this uncertainty lies the essence of astrophysical inquiry, the ability to read motion as memory, to decode light into history, and to see in a single galaxy the echoes of formation, collision, and cosmic equilibrium. NGC 2685 is not static, despite its seemingly stable appearance. Beneath the calm rotation lies a subtle interplay of evolving forces, dynamical friction, gravitational torques, internal pressure gradients, that may, over cosmic timescales, alter its structure in imperceptible but accumulative ways. The polar ring, although kinematically stable now, is not immune to secular evolution. Star formation depletes its gas reservoir, stellar feedback injects energy into the surrounding medium, and slow interactions with the galactic halo can induce vertical thickening or gradual orbital decay. These processes are slow, occurring over hundreds of millions of years, but they act continuously. The present form of NGC 2685 is therefore transient, not fleeting, but evolving in a slow gravitational rhythm that defines its long-term destiny. Gravitational instabilities within the ring, although largely suppressed by its relatively low mass and high orbital velocity, may occasionally lead to local condensations, regions where the balance between pressure and self-gravity is tipped, giving rise to massive star clusters. Over time, these clusters may drift inward due to dynamical friction or migrate outward under the influence of radial pressure gradients. Their orbits, slightly perturbed by asymmetries in the mass distribution or halo shape, can begin to precess, tracing out rosettes in phase space that contribute to the diffuse stellar halo. This migration can seed the formation of faint stellar bridges between the polar ring and the central spheroid, slowly weaving the two components into a more unified stellar structure. On larger scales, the interaction between the polar ring and the hot, diffuse circumgalactic medium may also be significant. If the galaxy resides in a region with low-density intergalactic gas, as is often the case in field environments, then ram pressure stripping is minimal, allowing the ring to persist undisturbed. However, should NGC 2685 move through a denser medium, or experience infall into a group potential, even low-level pressure can begin to erode the ring's outer layers, peeling away cold gas and quenching future star formation. This would effectively fossilize the ring, transforming it from a site of ongoing stellar birth to a fading stellar relic, still rotating, still orthogonal, but no longer evolving actively. The central spheroid, meanwhile, shows little sign of disruption. Its stellar population, dominated by older, redder stars, rotates smoothly with low-velocity dispersion, suggesting that the core structure was already dynamically relaxed before the ring formed. Its morphology, close to that of an S0 galaxy, indicates an early cessation of significant gas accretion and star formation. Yet even here, the gravitational influence of the ring is not negligible. Over very long timescales, mass redistribution via torques could alter the central density profile, potentially flattening the inner light distribution or inducing weak oval distortions. These feedbacks, although subtle, reveal how even a low-mass polar ring can interact with and slightly reshape the stellar architecture of its host. At the scale of the dark matter halo, the very existence of such a multi-spin structure places constraints on its isotropy. If the halo were significantly triaxial or clumpy, the ring's coherence would likely not survive. The observed longevity of NGC 2685's ring suggests that the halo is smooth, with low levels of substructure, and at least quasi-spherical in shape. This is consistent with lambda CDM predictions for halos of relatively isolated galaxies, but remains a vital empirical data point in the broader debate about dark matter halo morphology and the role of baryonic feedback in shaping halo dynamics. Looking ahead, future observations of NGC 2685 could dramatically enhance our understanding. Integral field units such as μ's on the VLT or JWST's NIR spec could map the velocity fields of both the ring and the host in exquisite detail, revealing minute variations in stellar and gas motion that encode the gravitational potential shape. High-resolution radio interferometry with instruments like ALMA or the SKA could trace molecular gas dynamics and reveal the structure of cold star-forming regions within the ring. Combined with space-based photometry, these data could be used to construct full six-dimensional phase space models of the galaxy's structure, dynamics, and evolution. Such models would allow us to treat NGC 2685 not just as a snapshot, but as a dynamical system, one with memory, inertia, and long-term trajectories. By understanding how it arrived at its present configuration, and simulating how it will evolve, we gain not only insight into its own history, but also into the broader mechanisms by which galaxies absorb, assimilate, and stabilize external material. It becomes a paradigm for ordered complexity in the universe, a system in which merger, misalignment, and equilibrium coexist not in contradiction, but in gravitational harmony. The deeper we probe into NGC 2685, the more it reveals itself not merely as a morphological anomaly, but as a high-fidelity recorder of galactic physics operating under non-standard conditions. The orientation and structure of its polar ring allow astrophysicists to examine gravitational potentials in 3 dimensions, a rare opportunity in extragalactic studies. Most rotation curves and mass models derive from nearly coplanar structures, providing only partial insight into the shape of the dark matter halo. But in NGC 2685, the orthogonal geometry enables direct testing of whether the potential is spherical, oblate, or subtly triaxial, and how its shape varies with radius. These constraints feed directly into cosmological simulations, helping refine dark matter models on kiloparsec scales. Even more intriguing is the possibility that NGC 2685 may not be entirely alone in its configuration, but rather an observable survivor of a more common but ephemeral phase in galaxy evolution. In the early universe, where accretion rates were higher and angular momentum vectors more chaotic, many young galaxies may have temporarily harbored polar structures as gas fell in along misaligned filaments of the cosmic web. If true, then NGC 2685 might represent a fossil relic of a once common mode of gas accretion, a rare modern example of a galactic phase transition that typically resolved itself into more conventional disk geometries. Its preservation suggests not only that the conditions of formation were unusually favorable, but also that the subsequent dynamical environment remained benign enough to prevent rapid disruption. The galaxy's star formation history, both in the ring and in the host, offers another window into its evolutionary arc. Spectral energy distribution modeling across multiple bands, from ultraviolet to infrared, reveals distinct episodes of star formation, including a relatively recent burst within the polar structure. This episodic behavior implies that the ring's gas reservoir is not being consumed steadily, but rather in pulses, possibly regulated by local gravitational instabilities or feedback from previous generations of massive stars. Such a pattern may also be influenced by weak density waves or long-period oscillations within the ring itself, causing gas to compress and trigger localized starburst events. Over time, this may lead to a patchy, age-stratified distribution of stellar clusters along the ring, an observational signature that can be probed through high-resolution photometry and age dating of individual clusters. Chemical abundance patterns further strengthen the case for a complex, multi-origin system. Studies of emission line ratios in HII regions show that the ring is metal-poor compared to the central galaxy, but not pristine, indicating that while the ring originated from an external, less evolved source, it has since undergone internal enrichment through stellar nucleosynthesis. This enrichment traces a timeline. Each generation of stars contributes heavy elements back into the interstellar medium through winds and supernovae, gradually raising the metallicity. By mapping this enrichment spatially, astronomers can reconstruct a chemical evolution model for the ring, charting how star formation, gas recycling, and orbital dynamics interweave over hundreds of millions of years. Beyond purely physical considerations, the aesthetic and structural uniqueness of NGC 2685 also makes it a symbol of galactic individuality, a reminder that the universe is not built solely from archetypes, but from systems that diverge, adapt, and stabilize in unexpected ways. Its geometry, while seemingly improbable, obeys the laws of orbital mechanics with precision. Its survival is not an exception to the rule, but an expression of deeper symmetries in gravitational systems, symmetries that allow even misaligned components to coexist and co-evolve. With every new generation of instruments, new layers of information become accessible. Deep spectroscopic surveys may one day reveal diffuse halo stars drifting between the polar ring and the host galaxy, linking the two through ancient orbits and extended streams. Polarization studies of dust grains in the ring could map magnetic field lines, adding another dimension to the study of galactic structure under rotational shear. Even gravitational lensing, though subtle at this scale, could eventually help quantify the halo's mass profile if background galaxies are aligned just so. In all these cases, NGC 2685 remains a touchstone, a nearby, accessible, yet profoundly complex example of galactic diversity. Its future is likely one of gradual change. The polar ring, though stable, will evolve. Gas will be used up or dispersed, star formation will decline, and new stars will phase mix into a smoother distribution. Over billions of years, the distinction between the ring and the host may blur, leaving behind only kinematic relics detectable in high-resolution spectroscopy. But for now, it remains one of the few galaxies where the interplay of mass, motion, and memory is so clearly and beautifully displayed, an astrophysical structure where the fingerprints of cosmic interaction remain preserved in every orbit and every star. NGC 2685 stands as a rare testament to the universe's ability to balance complexity with stability, asymmetry with coherence. It is not merely a snapshot of a galaxy caught in an unusual state, it is a sustained, dynamic structure that encodes billions of years of gravitational history. In its double rotation, in its chemically distinct stellar populations, in its perpendicular orbits and quiet star formation, it offers a multidimensional record of how galaxies interact, adapt, and endure. As astrophysical instruments grow more powerful and simulations more precise, NGC 2685 will continue to serve as both a challenge and a guide, challenging our assumptions about structure and evolution, while guiding us toward a deeper understanding of how galaxies truly form and persist in a universe ruled by dark matter, gravity, and time. The Helix Galaxy is more than a curiosity, it is a cosmic archive, silently turning through space, preserving within its orbiting light the story of transformation, survival, and the beautiful strangeness of the cosmos.